Tutorial 8, question 3a. Integrate 3x minus 4 cubed. First thing we need to recognise about this integral is that it has a linear factor of x, which is 3x minus 4. So what we're going to do is we're going to replace 3x minus 4 with u. If we differentiate the left hand side, we'll get 3. If we differentiate the right hand side, we'll get du dx. With a bit of manipulation, you can see that dx is therefore equal to du over 3, which means that the integral now becomes the integral of 1/3 u cubed du. To integrate this, we raise the exponent by 1, so it becomes u to the 4th, and we divide by the new exponent, so we get the answer of u to the 4th over 12. Now we back substitute for u, so we get the answer is 3x minus 4 to the 4th over 12 plus a constant. Differentiation is easy, integration is not. So every time you do an integration of this kind, always differentiate it to make sure you get back to the question. So we're going to differentiate 3x minus 4 to the 4th over 12 plus a constant. Okay, to differentiate, we multiply by the exponent and then we reduce the exponent by 1. So we get 3x minus 4 to the 3. And then, because this is a linear factor, we have to multiply by the integral of the bracket, which is obviously going to be 3, which is where that 3 comes from. And then finally, we've got the constant of integration, and differentiating a constant will give you 0. So now we've got 4 times 3, which is 12, divided by 12, so the 4 times 3 cancels with the 12, giving us 3x minus 4 cubed, which is where we started. Question 3b. Integrate 1 over 5x minus 2 cubed dx. Well, like the previous example, we have a linear factor of x here, which is 5x minus 2. So we'll replace that with u. 5x minus 2 equals u, so dx equals du over 5. Substituting these into the integral, we get I is equal to 1 over 5 u to the minus 3 du. Notice that 1 over u cubed is the same as u to the minus 3. As before, we increase the power by 1 and divide by the new power, so we're going to increase minus 3 to become minus 2, and then we're going to divide by minus 2, giving us 1/5 u to the minus 2 over minus 2. And then if we substitute the value of u, we're going to get minus 1 over 10, 5x to the minus 2 squared, plus a constant of integration. For the sanity check, we're going to differentiate minus 1 over 10, 5x to the minus 2 plus a constant. Well, to make it easier on ourselves, let's take the 5x minus 2 squared onto the numerator. The constant of integration will disappear. To differentiate, we multiply by the power and then reduce the power by 1. We'll get minus 2, 5x minus 2 to the power of minus 3 divided by 10, and then we have to multiply by the differential of the linear factor, which is going to be 5. That's where that 5 comes from. So the minus and the minus will cancel. 2 times 5 is 10. There's a 10 there, which means that we're left with 1 over 5x minus 2 cubed, which is what we expected. Part C. Integrate 3 to the power of 4x plus 1. 4x plus 1 is a linear function of x, so we're going to replace it with u. 4x plus 1 equals u, so dx is equal to du over 4. Substituting these into the integral, we get I is equal to 1/4 3 to the u du. This integral can be found on the table of standard integrals to be 3 to the u over 4 log 3. If we substitute for u, we get 3 to the 4x plus 1 over 4 log 3 plus a constant of integration. To differentiate this expression, we need a trick. What we're going to do is we're going to take e to the log of 3 to the power of 4x plus 1. E to the log are inverse operations of each other, so it's a little bit like multiply divide, which means that we've not actually changed the expression, but we can't differentiate 3 to the power of 4x plus 1. We can differentiate e to the power of a function of x. And then there's one final trick. We've got log 3 to the power of 4x plus 1. We can bring the exponent outside of the log like this. Now we're in a position to differentiate. So the differential of an exponent we know is the exponent. Then we have to multiply by the differential of the exponent. Well, differentiating 4x gives us 4, so we end up with 4 log 3. 4 log 3 on the denominator, 4 log 3 on the numerator means that we can now write e to the 4x plus 1 log 3. So we'll now raise that to the power, and then we'll cancel the e and the log, giving us the answer we were looking for. Integrate e to the minus 3x cos 2x dx. Because we have a product of two factors, what we're going to use is integration by parts. So we'll let u equal e to the minus 3x, so du dx is equal to minus 3 e to the minus 3x, and we'll let dv dx equal cos 2x, so v equals sine 2x over 2. As usual here, we should pause and differentiate just to make sure we get back to here. So the differential of sine 2x is going to be cos 2x times the differential of 2x, which is 2, which would cancel the 2. So the differential of sine 2x over 2 is going to be cos 2x, which is correct. The integral is equal to u v minus the integral of v du dx. We'll take the constant values outside of the integral sign. We've got a minus and a minus, which gives us a plus. We've got a 3 there and a 2 there, so that gives us plus 2/3. Now we have another integral similar to the first one. So let's call this equation 1, and we'll let this part equal I1. Now u1 is equal to e to the minus 3x, so du1 dx equals minus 3 e to the minus 3x, and dv1 dx is equal to sine 2x, so if we integrate that we get minus cos 2x over 2. Differentiating cos 2x will get minus sine 2x over times 2, so differentiating minus cos 2x over 2, we're going to end up with sine 2x, which is correct, so we can continue. So now we're going to get that I1 is equal to u1 v1 minus v du dx. In the first term we've got a negative inside the bracket here, so we'll take that outside. We have a negative here, times a negative here, times a negative here, which means that this part of the expression is negative, and we have a 3 and a 2, so we'll take those outside of the integral sign, which means that I1 is equal to this expression. Now look at that and look at that. They're the same, which means that I can replace the integral with I. That's going to be our second equation. What I'm going to do now is to insert equation 2 into this part of equation 1, giving us I is equal to e to the minus 3 sine 2x over 2 plus 2/3, and then I'm using square brackets outside, e to the minus 3x cos 2x over 2 minus 2/3 I. On the right hand side I've got e to the minus 3x over 2 in the first term, and I've got minus e to the minus 3x over 4 in the second term. So I'm going to take e to the minus 3x over 4 outside of a bracket, giving me 1 plus 9 over 4i, e to the minus 3 over 4, and because I've taken 4 out, I'm going to end up with 2 sine 2x for the first term, and there's a 3 here and a minus there, so I'm going to get minus 3 cos 2x for the second term. If I put this over a common denominator, I'm going to get 4 plus 9 over 4, which is 13 over 4. Those denominators will cancel, then I'll divide both sides by 13 to get rid of that, giving me e to the minus 3x over 13 outside 2 sine 2x minus 3 cos 3x plus a constant. Now we'll differentiate this expression to make sure we get back to where we started. The differential of e to the minus 3x over 13 brackets 2 sine 2x minus 3 cos 2x. This is of the form u v. So the differential of the exponential term is going to be minus 3 e to the minus 3x over 13 times 2 sine 2x minus 3 cos 3x. Then we're going to add to that e to the minus 3x over 13 times the differential of this bracket, which will give us 4 cos 2x, and because that's a cos we'll end up with a plus sign here, so it's plus sine 2x. We've got e to the minus 3x over 13 in the second term, and we have minus 3 e to the minus 3x over 13 in the first term. So let's take e to the minus 3x over 13 outside of a bracket, and then taking that minus 3 in there, I'm going to get minus 6 sine 2x plus 9 cos 2x, and then I have the second terms here, 4 cos 2x and 6 sine 2x. 6 sine minus 6 sine, so they cancel. 9 cos plus 4 cos is going to be 13 cos, so that will give me e to the minus 3x cos 2x, which is correct. So we can have a nice red tick. Part E. Integrate e to the minus at sine omega t minus phi dt. This is in effect the same as part D, except this time we're differentiating with respect to t rather than with respect to x. Okay, so we're going to use integration by parts again. So we'll let u equal e to the minus at, so du dt is equal to minus a e to the minus at, and we're going to let dv dt equal sine omega t minus phi, so v equals minus cos omega t minus phi over omega. If we differentiate cos omega t minus phi, we'd get minus omega sine omega t minus phi, which means that if we differentiate minus cos omega t minus phi over omega, that's correct, so we can continue. So that means I is equal to u v minus v du. In the second term we've got 1, 2, 3 negatives, so that ends up as negative. We've got a on the numerator and omega on the denominator, so we can take a and omega outside the integral sign, giving us a over omega e to the minus a omega t times the cosine of omega t minus phi dt. We'll call that equation 1. Then this section we're going to call I1. So let I1 equal that, and so u1 is going to equal e to the minus at, so du1 dt is equal to minus a e to the minus at, and dv1 dt is going to equal cos omega t minus phi, so that means v equals sine omega t over omega. Let's differentiate sine omega t minus phi over omega. We're going to get cos omega t minus phi times omega which will cancel with that omega, so that's correct, so we can continue. So that means I1 is now equal to the expression here. We've got a minus here and a minus here, which means that this term is going to be positive. We've got an a here and an omega here, so we can write that the integral is equal to e to the minus at sine omega t minus phi over omega plus a over omega e to the minus at sine omega t minus phi dt. Notice that this part of the integral is the same as where we started, so we can replace that with I, and that's our equation 2. Now we need to insert equation 2 into equation 1. I is equal to minus e to the minus at cos omega t minus phi over omega minus a over omega outside e to the minus at sine omega t minus phi over omega plus a over omega times I. So the first thing we're going to do is to move the I term onto the left hand side. We've got minus a omega here, we've got a omega here, which means we've got minus a squared over omega squared, which when we move it onto the left hand side we'll end up with plus a squared over omega squared. And then we have a minus e to the minus at here and a minus e to the minus at here. So we'll take that outside of a bracket. So we've got minus e to the minus at over omega squared. We have a single omega here, so I need an omega in the numerator. And here we've got omega and omega, so that's the omega squared gone out. And I've got an a outside the bracket there, so that's a sine omega t. The left hand side, we'll put that over a common denominator, so we're going to get a squared plus omega squared over omega squared. The omega squared will cancel from both sides, and if I divide by a squared plus omega squared, I'll get the answer. And of course we have a constant of integration. Is it right? Well, this is time for a sanity check. This is clearly a product. To differentiate the first term, we're going to get minus e to the minus at times minus a. So that gives us a e to the minus at over a squared plus omega squared times the bracket. Then we'll differentiate the contents of the bracket, so we'll get minus omega squared sine omega t minus phi plus a omega cos omega t minus phi. We have an a outside of the bracket here, so we're going to get a omega cos omega t minus phi, and we have a minus outside this bracket here, so that will give us minus a omega cos omega t minus phi. So that term will cancel with that term. We're going to get an a squared sine term here and an omega squared sine term here. So we'll take a sine omega t minus phi outside of this bracket. We've now got a squared plus omega squared on the numerator and a squared plus omega squared on the denominator, so obviously they will cancel, and we've got e to the minus at sine omega t minus phi, which is correct.